Today, I want to begin what I hope will be a series of talks on arcane topics in physics. What do I mean by this? Well, perhaps a Venn diagram will be helpful. There's a set of things, set of topics that often show up in textbooks. So represent that over here. And then there are all the topics that are not typically covered in textbooks. And this is what we will mean here by arcane. So they're way over here. And why do we do this? Well, there are lots of textbooks. This subject matter has been covered very well. On the other hand, there are all sorts of interesting, at least to me, perhaps to you as well, topics that are not typically covered in textbooks, and that is what we will attempt to address in these talks. Okay, so with those preliminaries behind us, let's discuss what is the topic for today. The topic for today is something called the why is this not working? The Terrell-Penrose effect. This topic is associated with the larger topic of special relativity. The science of objects moving at very high speeds, speeds that may be approaching the speed of light. And why does this interest us? Well, again, it's arcane and doesn't show up in textbooks, generally speaking. That's point number one. Point number two, it's kind of a paradoxical effect. And I'll explain why it seems paradoxical. It's paradoxical, first of all, because it is, first and foremost, a fundamentally visual effect, an optical effect, if you will. And yet, it is, for all practical purposes at least, invisible. So we have a visual effect which is invisible. That's rather bizarre, right? I think it is. Anyway, that's another point. Here's another point about it. It's very well understood. There are no mysteries here, really. It's very well, and it's the theory, as you will see later, is quite accessible. It's, as physics topics go, this is one of the less challenging topics, and it's very simulatable. You can simulate this effect quite easily, and we will show how you can do that. And again, despite all of these things, it's never been directly observed to my knowledge. So that's rather peculiar, I think, and worthy of a more detailed discussion. The Terrell-Penrose effect. Well, it is simply this. If I have a rapidly moving object, a rapidly moving object, and by rapidly I mean approaching the speed of light, which is a rare thing, of course, hard to achieve. A rapidly moving object appears to an observer deformed. In other words, its shape is distorted. That is it in a nutshell. And the idea can be understood in terms of two effects. One of these is called Lorentz contraction. Lorentz contraction. And what Lorentz contraction tells us qualitatively, at this, we'll just be qualitative for now, has the effect that an object is contracted in the direction of motion. That is a central result of special relativity. And then there's another effect which we could give the short name of latency. You may be familiar with the term latency from the use of computers. Latency is like, how long does it take for a ping signal to return to you when you are on a computer? Or how long does it take after you hit the carriage return for a calculation to complete, or something like that? It's a time delay. So it's a time delay. In this case, it's a time delay due to the finite speed of light. So another way of saying this is that if the speed of light were infinite, there would be no latency. It's the fact that light speed is non-infinite that you have latency. So anyway, these two things, this and this, together give you the Terrell-Penrose effect. What do we want to do now? What I'd like to do next is show you how, in practice, things deform. So we're going to look at different shapes. We'll look at circles. We'll look at lines. We'll look at cubes, and so on. Moving, all of these things would be moving at velocities v approaching less than, but not much less than, c, the speed of light. And we want to do is show you how these things look. And for that, we're going to need some simulations. So simulations. So that's what we're going to do now. So we are now in our simulation environment for the Terrell-Penrose effect. Okay, so let's first try to explain what this display is. So over here on the left are a series of parameters which we can use to control our simulation. So we can control the position of the object of interest, which in this case is a cube. You can control its speed. We can control, in this simulation environment, something we cannot do in reality, which is the speed of light. We can actually change it, but we've set it to 1. So we're in units called natural units where the speed of light is 1. We can control the size of the object, the number of sources that make up the object, these points. We can turn on and turn off Lorentz contraction. Okay? So that's what the controls are, and we can also choose the shape that is of interest to us. All right, now over here we have a window that shows us the apparent positions of all these points of light. And it's displayed in 3 dimensions, as you can see here. So this is not something that a human being can see directly. You can think of it as the God's eye view. And then over here on the right, we have what we would see. This is what the image that would be presented to us if we were located here at this black dot, the origin of coordinates, equipped with a telescope, looking at this object. Okay? So that's the layout. Now, let's, and as you can see right now, nothing out of the ordinary is going on. The cube does not look distorted in either view. What you're seeing here, of course, is the effect of perspective. One edge of the cube, this edge, is closer to the observer, to the telescope, than the other, and that's why it appears larger to us, okay? So again, there's a telescope here looking at this, and this is what the telescope sees, okay? So now let's play around with this a little bit. Right now, the speed is very small, 1/1000th the speed of light, okay? Actually, that is already an extremely high velocity by almost any standard. But yet, even at this very high velocity, there's no obvious distortion in the shape of this cube. Okay? So let's now increase this speed a little bit, and let's see what happens. Now, if you look at that, you'll see a couple of things. On the one hand, in the left-hand display, we see the cube turning into sort of a parallelepiped, okay? Whereas in the right hand of the display, which is a 2-dimensional projection, we're seeing what appears to be a rotation. Sometimes people call that the Terrell-Penrose rotation, okay? And at extreme speeds, it actually flattens, in this God's eye view, it flattens the cube into a sort of a distorted and rotated square. And over here you can see it looks like a slightly distorted trapezoid. Another thing we can do is to change the position of this thing. So let's now change the position of this cube while maintaining this very high velocity of 0.999 times the speed of light. So we're very near the speed of light. Okay, and we're going to change the y coordinate. Oh, just to be clear, this is the velocity direction. So the object is moving toward the lower left. Okay, so let's now change the position of this thing. We'll start by moving it backward, if you will. Sorry, that's not backward, this is backward. You'll notice an interesting thing happening there. The object becomes more and more distended in the God's eye view on the left as it's approaching the observer, whereas over here, as it's receding away from the observer, it gets more and more flat. More and more flattened, if you will. Okay, so that's an interesting effect as well. Not least, we can turn Lorentz contraction on and off. Let's play with that. Remember that 2 effects work together to create this appearance. One is Lorentz contraction, which is the contraction of this object in the direction of motion, which is this way. There's also the latency effect. So what we're going to do is turn off the contraction effect to see how that affects the position of this, the appearance of this thing. So there we see that when you apply Lorentz contraction, this thing does indeed get substantially thinner, okay? And it has a very profound effect on the telescope view, as you just saw there, okay? Now let's try that same series of actions at a different position. Let's go to the point where it's, now we're at the point where the object is a little bit different position, approaching. It has a component of its velocity that is approaching the telescope. And now let's see what happens when we turn Lorentz contraction on and off. A very substantial effect. So Lorentz contraction is absolutely operating big time over here, okay? Very good. Now let's go to the position where the object is effectively receding from the observer. So here we are receding. Lorentz contraction is now on, but now we will do something that's very hard to do in a real experiment. We're going to turn off Lorentz contraction. And we see here again, Lorentz contraction has a very substantial effect on the appearance of this object. Okay, and now for our next demonstration, let's change the shape of this object. So remember, we're still moving at very high speed, very close to the speed of light. Let us now change from a cube to a sphere. So here we have now a sphere. And you may say to yourself, well, that doesn't look much like a sphere, at least over here in the God's eye view. That doesn't look very much like a sphere at all. But remember, we're moving at very high speed. So let's move the speed back down to near zero. And you see at near zero speed in the God's eye view over here, the coordinate view, if you will, it does indeed have a spherical shape to it. And then looking over here on the right to the telescope view, what the observer actually sees, we see again something that is has a circular outline, and we can imagine that this, in our mind's eye, that this is a sphere. Let's now crank the speed back up again and watch what happens. Whoops, that's the wrong one. Let's try this. Notice what's happening here. In the left-hand view, the coordinate view, the sphere is getting distorted in some way, but in the right-hand view, it looks like a rotation. So again, that is this phenomenon that they call Terrell-Penrose rotation, or Terrell rotation. Okay? So what does this mean? What this means is, and let's look at this from a different view. You can see Lorentz contraction is very much operating here. See how thin that thing is on the left. And if we turn off contraction, you can see that it regains some of its thickness. But in the right-hand view, what we can actually see as humans looking through telescope is something that still looks like a sphere. So this was an important result that was arrived at by Penrose, which is that a spherical object maintains a spherical appearance no matter what its state of motion. So we talked earlier about the paradoxical aspect of this effect, that it's more or less invisible, and this is one of the several reasons. No matter how fast we are going, a sphere looks like a sphere. And of course, most of the objects that we look at night are spheres. They are stars. So even a star that's moving very fast would not appear obviously distorted to us due to this effect, if there were any stars moving at that speed. Okay? So that's another point to be aware of. Let us now go to another case, which is the case where the object of interest is a circle rather than a sphere. And I'm going to choose a circle whose axis of symmetry is in the x direction. So here's our circle. So if you look here, you'll see in the coordinate display, the God's eye view, that we have a circle, and this is the direction of view from the observer, and you can see the observer is looking straight at the thing along its axis, and the circle is moving to the lower left. Okay? So now let's see what happens when we increase the speed in this case. Let's talk about what we expect. We know that the Lorentz contraction is going to want to make this, to compress this thing in the direction of motion, which is this direction right here. And then the latency effect will have a different effect, which is hard to explain. I will simply show you. Okay, so here we go. We're going to increase the speed. Did something funny. Let's start the beginning. Okay, here we go. Now here we are at 0.987 C. Let's make it exactly 99 C. So 1% less. So 99% of the speed of light. Here we are. And you can see that our circle has deformed quite dramatically. Now in the telescope display, what you would see in the telescope is something that has sort of a boomerang shape or a sickle shape. This is something that Roger Penrose predicted in his 1958 paper, actually. And over here you can see that Lorentz contraction has indeed compressed the thing in the direction of motion. We can verify that statement by doing this. I will turn off Lorentz contraction, and you can see that in the absence of Lorentz contraction, the latency effect actually causes the circle to elongate a little bit. So let's put that back on. So now let's make the speed even higher. Let's go all the way to 0.999. So we're now one-tenth of a percent less than the speed of light. You can see our boomerang has become even more pronounced, or sickle shape, whatever you want to call it. And then over here we see a similar thing as well. Okay? So again, going back to the paradoxical nature of this effect, consider the fact that we never see this. No one has ever reported seeing such a thing, to my knowledge at least. And there are a couple of reasons for that. Again, we're at very high speed, and there are no nearby astronomical objects that we know of, literally none, that are moving at this high of a speed. Okay? It's just an interesting fact about the conditions within our universe that we just never seem to see this. Interesting. Okay? Secondly, we're looking at a particular geometry here. We're looking at the case where the object is moving transverse to the line of sight. So this is the line of sight, this vector right here, and this is the direction of the velocity vector. So this is another thing, we never see objects. So we do see objects that are moving that seem to be moving this fast, but they are galaxies. They're very distant galaxies, okay? And galaxies that we see that are moving at this speed are never moving this way. They're always moving outward, away from us, along the line of sight. So again, the universe has contrived to keep this effect invisible to us, it seems. Okay, so that's enough with circles. Let's now go to another case. I'm going to put the our final case, I'm going to put the velocity back to a low value, and I'm going to go to the case of a line. And I'll start with a line that is in the z direction. Okay, here's a line. It's just a simple one-dimensional line. Okay, and in this geometry, the line of sight and the velocity vector and the line itself are all mutually perpendicular to one another. Okay, very good. So now let's increase the speed. But again, before that, let's think about this. Now, a line, we know that Lorentz contraction wants to compress things in the direction of motion, but now the line is perpendicular to the direction of motion. So we don't expect Lorentz contraction to have any effect whatsoever in this geometry. So this will be a nice little check. Okay? What we do expect is that the latency effect may do something, because these points at the ends of the line are further away from the observer than this point close to the middle. Okay? So we do expect latency to do something. So let's see what happens now as we increase the speed. And what we see is not entirely unlike what we just saw in the case of the circle. As expected, the Lorentz contraction is doing nothing. And let's just verify that. We'll turn it off and turn it on again. And indeed, we don't see any change. So Lorentz contraction is a null effect in this case, whereas latency is still present. Let's just make the velocity really high. So 6 nines. So that's what we see. The thing's moving very fast. And we do indeed, once again, get a sort of sickle shape or the arc of a circle, something of that nature. Okay? We can also change the type of line. Let's go back to small. Let's now take a line that is oriented in the direction of motion. This is another interesting case. So I'll go Y. So now the line is parallel to the direction of motion. Now let's see what happens here. Again, crank up the speed. And you can see that the line is indeed getting compressed. If we turn Lorentz contraction off, the line once again is restored to a much larger length. So Lorentz contraction is operating very powerfully here. Okay. Let's try modifying the position of this thing. We're going to first go over here. Let's go over here. Okay. What we see is that the apparent length of the line in this display over here changes with position, even though nothing else is changing. Okay? So that's kind of interesting. We also notice that portions of the line which are effectively approaching the observer are becoming elongated. This is a latency effect. So latency for an approaching object, latency wants to elongate the appearance of the object, while contraction, Lorentz contraction, always wants to make it shorter. So and then when the object is over here, both effects act together, Lorentz contraction and latency both want to make the thing shorter. And in fact, for very high velocities, a line looks like it has shrunk to a point. in both of these displays. Okay, so this concludes the simulations section of our talk on the Terrell-Penrose effect. Let us now go to another point. Let's return to the point having to do with the invisibility of this effect. Let's talk about why this visual effect is actually invisible. Okay? So let's talk about invisibility. Invisibility. Here we go. Invisibility of Terrell-Penrose effect. I'll just call it TP effect. So let's think about it from the lab point of view first. Let's say we have a laboratory that is equipped with all sorts of great equipment, and we have a large budget. So maybe we can do this in a lab. Well, the problem is the energy required needed goes to infinity as the velocity goes to the speed of light. Okay? So even a 1 gram object, let's say you wanted to do this cube idea. Let's say you had a cube that was 1 gram in size. 1 gram. The cost of this would far exceed, even in principle, any lab budget that you could possibly imagine. Someone put much greater than lab budget for any lab that you could possibly conceive of. So that's point number 1. Point number 2, even if you had the energy, let's say somehow you had a windfall and had this amount of energy available to you, the object of interest breaks apart. Accelerating something to the speed of light requires enormous forces, and these forces are too great for anything except the very tiniest objects. So we can accelerate, for example, particles such as electrons or protons. Okay, that's great. Things like, so I'll just say proton, electron, for example. But these are microscopically small things, and we can't see them in the traditional sense because of their small size. Okay? So, any hope of seeing the Terrell-Penrose effect in the lab is destined to be quashed by Mother Nature. Okay? But there's another thing we could conceivably do, which is to go to astronomy. There are lots of seemingly fast-moving objects in astronomy, right? Well, actually, not so much. Okay? In astronomy, there's nothing, no objects, no local, I'll explain what I mean by local, objects with velocity that is comparable to the speed of light. Literally none. In our galaxy, for example, There are things such as jets, which are emitted by black holes. These go fairly fast. Most things, the velocity scale for local objects is on the order of hundreds of kilometers per second, which is, 1/1000th of the speed, on the order of 10 to the minus 3. So this is a velocity of on the order of 10 to the minus 3, where light speed is 1. So, sorry, no local objects. Now there are distant objects. What about distant objects? All sorts of things move away from us very fast that are distant, right? Well, in a sense, no. So, distant objects, galaxies. There are distant galaxies which have high redshift, which have very high redshift. And if you interpret this as a Doppler effect, then you could say the velocity as measured by treating these things as Doppler effects is indeed on the order of c, okay? But, and it's a big but, this is actually not a special relativistic effect. It's actually not a Doppler effect. So this is actually incorrect to think of it this way. What we are seeing is an object which has experiencing the results of what is called the Hubble. This is the result of the Hubble expansion of the universe, which is an entirely different effect, somewhat related, but an entirely different effect. Okay? So, bottom line, distant galaxies, not going to help you much either. And then, of course, we have the Penrose result that spheres, that didn't look so good. Spheres map to spheres under the Terrell-Penrose effect. So even if there were a star somewhere that was moving at a highly relativistic speed, say transverse to the line of sight, it still wouldn't look any different to us because it still would look like a sphere. So the bottom line is that we really can't see the Terrell-Penrose effect. The Terrell-Penrose effect is indeed invisible. Terrell-Penrose effect is invisible. Bizarre, but true. Okay? So, up to now, our presentation, just a couple of concluding remarks here. Up to now, the presentation has involved no mathematics to speak of. I will address the math in the next video on this topic. So until then, be well and talk soon.